Hello and welcome to this video on an introduction to matrices and some basic operations involving matrices. This is going to be the first in a series of videos about matrices where we're going to see how we can use matrices to express a system of equations like this one here and express them in matrix form like this. We'll talk in later videos how we'll use matrices to solve this system of equations and find these unknown terms x, y and z. But in this video let's concentrate more on what a matrix is, how we can construct matrices and some very basic examples of some operations that we can perform. So first of all, we give the dimensions of a matrix m by n. So m here represents the number of rows that a matrix has, and n represents the number of columns. So here you can see that the first matrix that we have in our equation here is a 3 by 3 matrix. It has 3 rows and 3 columns. Here we have a 3 by 1 matrix and a 3 by 1 matrix here too. Inside the matrix, the different terms that make up our matrix are called elements. Elements can be numbers, but they can also be unknown values or symbols, or even complex numbers. We're going to return to systems of equations like this in later videos, but for the purposes of this video, let's start by just performing some very simple operations using matrices. We're going to look at how to add, subtract, and multiply matrices. So if we have two matrices whose dimensions are the same, we can add those two matrices together. So here we have two 2 by 2 matrices because they each have 2 columns and 2 rows. And we're going to add those two matrices together. The method is very simple. All we do is we add the corresponding elements from each matrix. So for example, the top left element in the first matrix will be added to the top left element in the right-hand matrix, and so on and so forth. So to write this out in full, we'd have something like this. We'd see that our first top left element would be 2 plus 1. In the bottom left, we'd have minus 5 plus 7. In the top right, we'd have minus 3 plus 6. And in the bottom right, we'd have 4 plus 2. And of course, we can evaluate each of those to get our final result, which is going to be, well, 2 plus 1 is 3, minus 5 plus 7 is 2, minus 3 plus 6 is 3, and 4 plus 2 is 6. We can use a very similar method for subtracting matrices. So here again we have two matrices with identical dimensions. They're both, in this case, 3 by 3 matrices. And this time we're going to subtract, which means subtracting the corresponding elements from each matrix, 7 minus 11, and so on and so forth. And so if we write this out in full, we'll see something like this. And then we can go ahead and evaluate each of these elements. One thing to watch out for is any double negatives. So here, for instance, in the top right elements, we have 3 minus 5. So that double negative is going to result in an addition rather than a subtraction. But anyway, let's move this up just slightly, and we'll find that this evaluates to this. Again, just be careful to watch out for the double negatives where they occur and make sure that we've calculated the right results there. So there's an example of subtraction of matrices. One final thing to mention, which I've not mentioned before now, is you'll notice that every time I write out a matrix, it's enclosed in square brackets. Sometimes you'll see examples in textbooks and so forth that use square brackets. Some just use normal parentheses instead, but usually a matrix is enclosed in either of those two forms, either in square brackets or just normal brackets. So finally in this video we're going to look at multiplication of matrices, but we're going to look at two different types of multiplication. And the first is what we call scalar multiplication. Here's an example of scalar multiplication. And we bring this up first because it's the simpler of our two types of multiplication that we're going to look at. And in this case, all we're doing is really multiplying the elements of a matrix. Here we have a 2 by 2 matrix. We're multiplying them by a scalar, a number. In this case, we're multiplying each of the elements by 2. So scalar multiplication, very easy, because all we're going to do is multiply each of these elements. We'll see that we get 2, 12, 14, and 4. And that's still a matrix enclosed like so. It doesn't have to be an integer number. It could be a non-integer as well, but the same process applies. We multiply each of the elements by whatever it is that we're multiplying by. So we saw that the method of scalar multiplication was very simple, and that's the reason we mentioned it first. But the next type of multiplication that we're going to look at is matrix multiplication, where we're looking to multiply two matrices together. So let's use these two matrices as an example. Let's say we've got matrix A with the elements 5, 3, 2 and 7, and the matrix B which has the elements 4, 6, 8 and 1. And what we're going to do is we're going to multiply these two matrices together, and we're going to write this as A dot B. And the reason we use the dot is because we're going to use a technique later on called the dot product in order to multiply these two matrices together. What we're not allowed to do is, if we write these matrices out like so, we're not allowed to multiply the corresponding elements 5 times 4, 3 times 6 and so on, like we did with addition and subtraction. Instead, we've got to use this method called the dot product, which is why we use this dot by convention when we're representing this type of multiplication. So let's have a look at how the dot product works. For now, I'm going to put this dummy answer below our multiplication here. The elements in this matrix are just placeholders for now, but you'll see that we've called them x11 because they're in the first row and the first column, x12 because it's in the first row and the second column, x21 because it's in the second row and the first column, and finally x22 is in the second row and the second column. Calculating each of these values is where the dot product comes in. And let's take the first top left value here, x11 that we've called it for now. Notice that x11 is in the first row and it's in the first column. And so what we're going to do is we're going to take the values from the first row of the first matrix and the first column of the second matrix. So we can express x11 as being something like this. We've got, here I've just written the values from our first row, 5 and 3, in the first matrix. And again, we see the dot for the dot product. And then we've got the values for the first column of the second matrix, 4 and 8. We still haven't said what the dot product is. The dot product is very simple. All we're going to do is, with our two sets of numbers here, we're going to multiply the first values together. So we have 5 times 4. And we're going to add that to the second values multiplied together. So here we have 3 and 8 are the second values from each set. And 5 times 4 plus 3 times 8 gives us a result of 44. So now we've worked out the value of x11, the first of our unknown terms in our resulting matrix, we're going to apply exactly the same method to x12, x21 and x22. So looking at x12 now, you can see that that's in the first row still, but it's now in the second column. So applying the same method as we saw before, because we're in the first row and the second column, we're again going to take the first row from our first matrix, 5 and 3, but we're going to take the second column from our second matrix, which is 6 and 1. So again, we can write them out like this. We can say that x12 is the dot product of 5 and 3 and 6 and 1. And from these two sets of numbers, we are going to calculate the dot product by multiplying the first two numbers together, 5 times 6, and adding that to the second numbers, 3 times 1. And again, when we calculate the result, we get 33. Let's follow the same method for x21 and x22 as well. So x21 is in the second row, but it's in the first column. So we'd see something like this, where we have 2 and 7 from the second row and 4 and 8 from the first column of the second matrix. And the dot product of those two sets of numbers gives us 64. And finally, x22 is in the second row and the second column. And so we have the dot product of 2 and 7 and 6 and 1, which we can write out like this. So now we have all of our unknown values. We can put them into our resulting matrix, and we've successfully now found the matrix multiplication of these two matrices as shown. Let's have another example of matrix multiplication. And here we have two more matrices, which we've called P and Q. But this time, the matrices are of different dimensions. So our first matrix here is a 2 by 3 matrix. It has 2 rows and 3 columns. And we're multiplying it by a 3 by 2 matrix. And so we want to find P dot Q. So the first problem here is, how do we know the dimensions of the resulting matrix? Is our result going to be a 2 by 3 matrix? Is it going to be a 3 by 2 matrix or something else? There's two important rules to remember when we multiply matrices together. The first rule is that if we're going to multiply successfully, the number of columns of the first matrix must be equal to the number of rows of the second matrix. So if you have a look here, our first matrix is 3 columns and our second matrix has 3 rows. And so we're going to be able to multiply these two matrices together. If this isn't the case, then our method for matrix multiplication doesn't work. The second rule to remember is that the result of matrix multiplication will have the same number of rows as the first matrix, and it will have the same number of columns as the second matrix. So our example here, the first matrix has 2 rows and the second matrix has 2 columns. And so our result is going to be a 2 by 2 matrix, similar to the last example. We're going to follow exactly the same method as in the previous example. So let's have a look first of all at x11. So x11 in our sort of dummy placeholder matrix here is in the first row and it's in the first column. And so we're going to take the first row of our first matrix, which is 2, 7 and 6, and we're going to take the first column of our second matrix, which is 9, 6 and 2. And what we're going to do is take the dot product of these two sets by multiplying the first terms from each set, 2 times 9, adding that to the multiplication of the second terms, 7 times 6, and then finally adding the multiplication of the last terms, 6 times 2. We'll not go through the whole working, but we'll repeat this same process for each of these elements. And here's the working for each of these that you can see here. You can pause the video for a moment if you want to check that for yourself. But if we evaluate each of these elements, we'll get a result that looks something like this. Let's have a look at one last example of matrix multiplication. And this time we're multiplying two 3 by 3 matrices together. And following the rule in our previous section, the result will also be a 3 by 3 matrix as well. And so here we've filled out these placeholder terms like so, because we have 3 columns now and 3 rows. So we have these 9 placeholder terms labelled so. Again, we'll not go through the working for each of these, but we're going to follow exactly the same process as we saw in the previous examples. So calculating x11, for example, we'll take the first row and the first column from each of our two matrices that we're multiplying together in order to work out the resulting element, and the same for all of these different elements as well. The total result, we'll work out the dot product for each of these elements and write it out in full here. And again, you can pause this video if you want to see that in a bit more detail or go through it yourself. But the result will come out as something like this for these two 3 by 3 matrices that we've multiplied together. The very last thing to mention in this video is to show that matrix multiplication is a non-commutative operation. So a commutative operation is one that can be reversed with no effect on the result. So for example, 3 times 2 is the same thing as 2 times 3. Multiplication is a commutative operation. Division is an example of a non-commutative operation, because 3 divided by 2 is not the same thing as 2 divided by 3. So matrix multiplication is a bit like this. It's a non-commutative operation. To illustrate this, let's go back to one of our earlier examples where we multiplied two matrices we called A and B, and we found the result to be something like this. You can attempt this yourself if you want to prove it to yourself, but if we reverse those two matrices and follow the same method using the dot product, let's say we multiplied B times A, or B dot A as we write it, we'd find that the result changes. It looks something like this instead. So the order of operation when we multiply matrices together is important, and you can't reverse them without changing the result too. So I hope you've found this video useful. First of all, on an introduction to matrices and how we lay them out, but then how we can perform some basic operations such as adding, subtracting, multiplying matrices as well.